Hi folks, welcome back to Physics with Captain Rod here. So we're going to chat about number 26 in Unit 3-2. So there's a picture of a square. I just drew it instead of copied it. That's rotating here. It's rotating at some angular velocity, so that's an angular speed. It'll have units of radians per second. That's describing how fast this is rotating. And it's rotating in a horizontal magnetic field, which is stated in the problem. So I put that here in this picture. So this loop, or this thing as it goes back and forth, its flux is going to be constantly changing. And the picture on the right, if we do a top viewpoint of this, like looking down, this is what we would see. Like this is this. And it would be rotating, right, at some angular speed here. And I drew a couple of vectors, the two most important. So here's our magnetic field vector, and here's a vector which is normal to the area. And the magnetic flux through that loop is equal to BA cosine theta. Field strength times area times cosine of the angle between the magnetic field and the normal. Now that angle's changing. In fact, the angle theta, let me write this. Let's see, BA. We can write the angle theta as omega t, because the omega there, that's the angular speed in radian per second, times t gives the angle in radians. So I actually drew a graph over here. That's a cosine wave. It's going to look something like that, flux against time. The flux is a maximum when theta is 0. That would be here on our graph. The flux is 0 when theta is pi over 2, or 90 degrees, and that's the red one in the graph. Then when theta is 180, you got to imagine when this normal is rotated all the way to this direction, we would have maximum flux again, except it's from the other way, I guess, if you will, and that's why I put it down here, minus sign. And then when this normal is straight down, no flux, and so forth. Now, by Faraday's law of induction, the induced voltage, remember, is rate of change of magnetic flux, right? Or in other words, change in magnetic flux over change in time. Now that's per loop. If there are more than one loop, you can basically put an n in front of it for the total number of loops there. And the next graph here, okay, is a graph of the slope of this one, because that's what this is. Delta phi over delta t is the slope of this graph. Now, I did this kind of to point this out here. In green, these are where the fluxes are a maximum, but the slopes would be 0. That's why this graph, I put it in green here. Here, that corresponds to that point, and this one corresponds to the, that point. And in red, that's where the slope is the steepest, there and there. And that corresponds to this, where the flux is a max, and and there, where the flux is a max, and so forth. So if we were to graph the rate that the flux is changing, it would look like this. And that's a sine wave. And that's why the voltage is sinusoidal. When I try to attach functions to it, that means the voltage has to look like this, V max sine omega t. Where the V max is in our graph here, whatever this maximum voltage is. Now, getting from here to here, I'm going to skip a lot of the math, but just think about the factors that are affecting this, right? Why is there a voltage? Because we are rotating, so this is causal. And ask yourself, if I rotate faster, do I expect a larger voltage? Hopefully the answer is yes. All right, we need the magnetic field because it's that QV cross B force that produces this effect. To get a magnetic flux, we need an area. Right? And then it's also dependent on n, the number of loops. And if you look at the product of all of these, it will actually work out the volts, right? So the maximum voltage is equal to this product, NBA times omega, sine omega t. Number of wires times field strength times area times radian per second. This will come out to voltage. Now this question says something about what is the maximum voltage. That's this product here. So kind of a long-winded explanation, but again, this is important stuff here. So I hope that this helps. Have a great day.